I got a Bushmulcher in the workshop, as we did well done new knives last summer somewhere, but we got an imbalance issue. Well, that was to be expected, but it means I need to get these old knives off as they have no purpose anymore, and at this moment they are definitely causing an imbalance. So I want them all off, but I know they are really stuck. So I already tried it this summer, but now the conclusion is they have to come off. So these axles, they have a special bolt hole, and I already made a bolt in there, and you see this. What we're gonna do is take this outside and pull on it with the forklift, as I got no other option at this moment to try to get rid of it. So I'm gonna attach a chain to this and then give it a pull with the forklift a few times, see if it wants to come or not. If it wants to come, then we're really lucky and we're able to get it out. So we're gonna install a metal plate here, which we can bolt off once we're done. But for now, we're gonna put a sensor in this hole, and with that sensor we can measure the position of this bolt. Right. Set up to measure the Bushmulcher. So we got two accelerometers on there, and both are measuring the accelerants in the Z direction. So it means if the machine flies up and down, it will be measured by an analog value with a frequency over 1 kHz. So we should definitely pick up the rotation, which is going to a max of 1000 RPM, and 1000 RPM is only 15 or 18 Hertz, something like that. So it should be quite fine, and that means we get a lot of measurement data, and we should be able to see where we have our imbalance and how to fix it. We also got this sensor mounted here. So this sensor will detect the bolt that I made on there, and every time it passes here I know it's this position. So I also know on the oscilloscope at what point we have what kind of imbalance, so I can figure out on which degree exactly our maximum imbalance is, so that I know where we have to fix the imbalance. I use two accelerometers, so I can see if there's an imbalance on the left and the right side of the roll, or where exactly it is, so we can figure out where to fix it. I brought a power supply, which I need for that sensor. We got another power supply for an Arduino. Arduino is powering the two accelerometers, and I brought two oscilloscopes. So this one is a digital one and this one is an analog one. I wired them both up so I can see the signal quite clear, and it also makes things a lot easier if you have to. So we're gonna have a look if we can trace down where the imbalance is. To explain what exactly I'm gonna do, I made a simulation in the program Scratch, which is actually a program for kids to learn coding, but it also perfectly visualizes what I want to explain. So I made it in Scratch, and I think this will explain very well what I'm gonna do. So here we got a rotor of a Bushmulcher together with a pulley. I got a sensor that we attached on it, and you just have to imagine that we put one accelerometer on top of here, and in real we have two, so we have two of these graphs. Here I made only one to keep it a little bit clear of what I'm gonna do. So now we're able to rotate the Bushmulcher, and it will just rotate, and if this bolt here comes by this sensor, the sensor will actually be active, and we can see that active signal on our oscilloscope, and we can also trigger it on it. So that means our oscilloscope will freeze this image exactly like we see it here. And the next pulse is on this position. So we do know that we have one rotation here. And this shows very well the z-axis acceleration from top to bottom and bottom to top. So we have a positive g-force on 90 degrees and a negative one on 270. And that's exactly what we expect, because we have an imbalance, and we expect the imbalance to be just as much above the 0 degrees as below the 0 degrees, and it will also be from the same amplitude. It's the same imbalance but rotating around the machine, and it's also happening in the other directions, but we're measuring only one direction. So at this point we can see we're now at 0 degrees, and we also have 0 acceleration in the z direction. But if we would rotate another 90 degrees, we can actually see that we have a negative 1g at this moment. So it means that we have a lot of weight on this side, as it's actually pulling the drum down. So it means we have a force going down here. And if we keep rotating, you will see we have a 0 point right here again. But that 0 point is actually from the z direction, but in real the force is actually going towards the tractor. And if we keep rotating, we can also see we get a positive 1g force again once the drum rotates 180 degrees from where we had the negative 1g. This also explains us that we need to add weight on the opposite side of this arrow. Now, to do this in the real world, we do know that we have a 0 point. So this is the point that we can recognize on the machine when the sensor is high and the bolt is there. Then we can see we have no force at this moment. But I do know if we rotate 90 degrees further, so I do this by hand in the video every time. Now we have minus 1g, so I know the place where to add the weight is on top, and I need it on the rear side. So I see this image on the oscilloscope. I know I rotated 90 degrees, so I know where we are on the oscilloscope image. And to get the side on the rear side, I know I rotate another 90 degrees so that I can weld in weight here to fix the imbalance issue. Of course, this doesn't calculate how much weight to add, but we can estimate it a bit by the height of the g-force. So now if I draw in the weight, then you can see we made a weight here, and the force should be gone once we added the correct weight. If we then rotate, we can see that our g-force is also basically flattening out. It's never perfect, so I draw it a bit with a very slight wave. That way we can still see it rotate. And in real life we also never get it perfect, but we definitely improve it by a lot. So now let's go do this in the real world. Let's fire the tractor up and spin it slowly so we can see what actually happens. I really don't know how this is gonna look like. Well, I just spinned it up a bit, and it seems that this complete arm is shaking too much, and I'm getting that back on the scope. I can see all the vibrations of the thing. So I'm taking this off so we get as less as possible mass which is dancing around, and this is actually dancing around on the hydraulics. So take it off and it's gone. So we take it off and we will spin it up again and then see how it goes. Alright, let's spin it up again. So now we got nothing on top of here, so we should have a lot less vibrations. So let's give it a try. Well, that data just shows how much vibration we have. The maximum we get is 3 Gs, but it means it does that over 1.5 volt. So we now got 0.4 volts offset, which is like 0.8 G on a RPM of 521. That's why they could measure between the pulses from the speed sensor. So now we know that it's running 521 RPM, what I just did, and we already get 0.8 G, which is a lot. You should not be getting that on your machine, that's not usual. And that's actually on the frame, it's not even the rotor itself, it's the frame. So it's 1000 kilos going with 0.8 G. We don't like that. That's causing a lot of damage if you run this for a long time. So we're gonna have to fix this. Now on the graph you can see exactly at which point, so in which point in time we have this 0.8 G offset. And because we know how much rotation we get by time, we can translate this to how many degrees. By the looks of the graph we can see here is our speed pulse and here is our next one. So we're quite in the middle with the highest point in the graph. We can see a lot of other resonances happening there, but we're mostly looking at the slow sine wave, as that's the one which comes with the rotation of the rotor. So this is the highest point in that rotation, and it's actually the opposite of where the speed sensor is. So if you look in reality, our speed sensor sits here and the bolt sits now there, which actually means that our highest point, so the point where we get the most vibration, is on this side. So this is where the rotor is at the heaviest, because we're now opposite of the measuring point. So this is exactly the point what we see on the scope. Now what we will need to do is to add some weight on this position on the left side of the rotor, as that's where we see the raise in the force. So let's take a look at if we can add some weight, and this basically is just trial and error. There's nothing I can do about it. Maybe there's a good method for it, but I don't know it. For me it's just experimenting to get this machine properly again. So let's see if we can add some weight and then get it properly running again. So because we know this machine is weighing in 11 or 1200 kilos, I'm gonna add the weights by the kilo at this moment, and then we're just gonna measure it again, as I really got no clue. I just know with this weight and this vibration we need to start big, and then we can see if we get the opposite result or something, and then we can figure it out further. So the place where we're gonna add it now is right in this spot, as there's space here. I mean, we can weld it and we can tack weld it a bit and spin the rotor up again, see how the balance is then, and we can play after it, but I can already compare how it does when we do this. What should be noticed is that even if we just have the tractor running and not run the PTO, we already got all kind of vibrations, and that's because we have an engine running. So the engine vibrations are actually being translated into the Mulsar. They are really small vibrations, as you can see, but still they are vibrations, and if the engine would have to work, these vibrations get worse, and that's what we see when we run the Mulsar, that these vibrations get worse as the engine is just working harder. If we look at the yellow line now, we can definitely see that we are improving, so adding the weight helps. I already added 2 kilos on the lowest point, so I will have to add another 2, I think. And then we can also see the blue line, which is also having quite an issue, so there we actually have to add weight on the opposite side. So we're gonna give that a try. Well, we got it running again. We're now at 800 RPM on the PTO. This results in having a pulse every 40 milliseconds. That means 25 Hz, so 1500 RPM on the rotor at this moment. And we're having quite a stable signal. It's not vibrating a lot. Still, I want to see if I get the last vibrations out as well. We do have a little bit now, but I already zoomed in a lot, so we got most of it out. I just want to level it out with the last grams. That's where it comes down to. We are now for the last bit of balancing, so we're gonna add this little piece on the correct spot and then test again and see if we need to add another one or half this to get it even more in balance. I know it's a bit overkill, but if you're on it, just do it properly. I'm amazed that this trick worked, as if you see, I added over 10 kilos of iron in that rotor, and we're now working with a piece you will see right now. "24 grams, that's exactly what's going on there. And yes, this scale is gram precise, so that's just amazing. That should be it. Let's give it a test. That's just phenomenal. So we got it leveled out now. You can hear some vibration because that hood is open and it's just so sensitive for resonant frequencies. But this is running really smooth. At 800 RPMs now on the PTO. We can rev up until 1200, so let's do that. And we will not note it on the scope, so that's perfect. So all these metal bits I had to add in, and they are at certain locations. That's just the process of balancing it. Well, just a little bit of self-reflection, but this project was just awesome. I thought that we would never be able to get this machine running properly again, but now we got it perfectly in balance. If you rev the machine up, you see absolutely no vibrations at all, just the vibrations from the sensor itself, because the sensor is always vibrating. We even got an engine running, and an engine gives vibrations, so even if the Bushmeister is off, we can see these vibrations. So it just worked out awesome. So I'm just really happy how this one worked, and I can't believe how nice it's running now. And it makes a really nice sound now if you rev it up until 1200 RPM. And 1200 RPM on the PTO is actually 2200 on the rotor. So being able to run this thing at 2200 RPM, that's awesome. It gives a lot of inertia to the thing, and the inertia is making this thing work. So we will have a lot of benefit from this machine again. If you're wondering why didn't I just replace the bits, well, you saw at the beginning of the video it doesn't want to let loose, so That's why, and also I wanted to get some more power to work in the ground, and this should definitely be able to do that right now. So we're gonna give that a big try out. If you enjoyed this video, don't forget to like, share and subscribe, and if you're curious, then just wait for the next video, as we got a lot more fun projects coming up. Thanks for watching.